In this video, we're going to look at the basics of absolute value functions. So let's start with the most basic absolute value function, y equals the absolute value of x. Now, absolute value is a function that behaves in two different ways depending on the original value of x. So I can actually define it as two different functions. Specifically, the absolute value of x will just be x if x is already greater than or equal to 0. But if x is less than 0, then I need the opposite of x. In other words, if x is negative, I need to make it positive. So basically, I have two linear functions, y equals x and y equals negative x, each of which is valid in a different part of the domain. So when I'm sketching this, I think if x is greater than 0, in other words, on the right-hand side of this graph, I draw the line y equals x. And so that's the line that goes through the origin and has a slope of 1. And if x is less than 0, so in other words, on the left-hand side of this graph, I graph y equals negative x. So that is a line still going through the origin, but in this case, the slope is negative 1. So this sharp angled shape here, these two lines mashed together, that's my absolute value graph. The origin in this case is the vertex, and that allows me to figure out what my domain and range would be. The domain is just going to be all real numbers because I can take the absolute value of anything I want. But the range is going to have to be values greater than or equal to 0 because the absolute value is always going to give me a positive value here. So the absolute value of x will always be positive. With those basic concepts in mind, let's move on to something a little more complicated. Now, we can understand what's happening with this function based on transformations, based on the information that we learned in quadratic functions, as well as with radicals. If I have something in this form, I can assume that what's happened is, I see this minus 2 in front here, so there's been a reflection. So in other words, this function is now going to open downwards instead of up. There's also been a stretch, so instead of having slopes of 1, I'm going to have a slope of negative 2. And I'm going to have a slope of 2. And based on the fact that it's going downward, the positive slope must be on the left and the negative slope must be on the right. And I can figure out where my vertex is based on the translations that must have taken place. The vertex must be at negative 1, because negative 1 plus 1 would give me 0, and negative 5. So with that information, I can already make a sketch. So negative 1, negative 5, opening downward. But I can actually figure out as well the equations of these two lines specifically. So if I think about what this would be, if x is less than negative 1, that's one side of this graph. And if x is greater than or equal to negative 1, that's the other side. In other words, the x value of the vertex is the critical value, or what value of x would make this expression inside the absolute value equal to 0. That's my borderline. So if x is less than negative 1, then x plus 1 is going to be less than 0, which means that the absolute value of x plus 1 has to be the opposite of x plus 1, which becomes negative x minus 1. So that means that y is now equal to negative 2 times negative x minus 1 minus 5, which I can simplify to y equals negative 2x minus 3. So that is the equation of the line on the left-hand side here, y equals negative 2x minus 3, although it only applies for values of x that are less than negative 1. So, for example, the fact that there's a y-intercept of negative 3 doesn't actually enter into play here because x isn't 0 in this function. On the other hand, if x is greater than or equal to negative 1, then if I take x plus 1, that's going to be greater than or equal to 0. So in other words, I get a number that's already positive, so the absolute value of x plus 1 just is x plus 1, which means that the equation in this part of the domain is just y equals negative 2 times x plus 1 minus 5, which simplifies to y equals negative 2x minus 7. If I look at the right-hand branch of what I drew over here, that is the second line, y equals negative 2x. Oh, sorry. I screwed up the first one. It should actually be positive 2x minus 3. This one is negative 2x minus 7. So positive 2x minus 3, I can see that line is going up. This one is going down, so negative 2x minus 7. And that y-intercept would be negative 7. All right, one more example. Again, using what we know of transformations, we can figure out where the vertex is. The vertex is going to be whatever x value makes this expression inside the absolute value equal to 0. So that would be 1. And then I can see there's been a vertical translation of 4. So my vertex is at 1, 4. I can also tell from the -3 that this is going to be opening downward, and the slopes are going to be positive and -3. But let's find specifically the two equations that we have. So I use the x equals 1 as my jumping off point. If x is less than 1, then 1 minus x is actually going to be greater than 0. So be really careful with this because we have a tendency to want to say, oh, if I'm on the left, then it's going to be negative. If I'm on the right, it's going to be positive. No, not the case. So if I take a number that's smaller than 1, for example, -17, 1 minus -17 is +18. That's a positive number. So that means the absolute value of 1 minus x just is 1 minus x. So in this part of the domain, the equation is y equals -3 times 1 minus x plus 4, which we can simplify to 3x plus 1. If, on the other hand, x is greater than or equal to 1, well, in this case, 1 minus x is actually going to be less than or equal to 0. So think about taking a number bigger than 1, 7, for example. 1 minus 7 gives me a negative number. So that means that the absolute value of 1 minus x has to be the opposite of 1 minus x, which you can write as -1 plus x. I'm going to write it as x minus 1, but they really mean the same thing. So that means y equals -3 times x minus 1 in this interval plus 4. So y equals -3x plus 7. So those are the two equations here. So I have a slope of 3, I have a slope of -3. One of those will end up being the y-intercept, but only the one where 0 actually is in the domain. So because 0 is less than 1, the y-intercept of this function will end up being 1. All right, so let's get a quick sketch of this graph. We know that the vertex is at 1, 4. We know that on the left-hand side of that vertex, the slope is positive. So we've got this line, and that this y-intercept has to be 1. And on the right-hand side, the slope is negative, so it's going down like that. And there is my graph. So we can treat absolute value functions much the same way we treated quadratics, and they do have a lot of similar types of characteristics. So for example, I have an axis of symmetry that goes through the vertex. So in this example, the axis of symmetry would be x equals 1. So the symmetry properties that I know about quadratics apply equally to absolute value functions of this type. I also know that the range is going to be dependent on whether this opens up or down and what the y value of the vertex is. So in this case, while the domain is always all real numbers, just like quadratics, the range in this case would be y is less than or equal to 4. So I'll do this one in interval notation. So I've got -∞ to 4.